Now, if you've ever tried to heat up your food, you may notice that in the microwave there's this rotating dish. It may seem like a fancy addition, but it's actually essential when it comes to heating up your food properly. Let's go and explore why. Before we do so, we need to understand what a standing or stationary wave is. Or standing waves do not move forwards or backwards. Like a normal wave may be transmitted from one place to another, standing waves are fixed in their positions, but they do oscillate vertically, upwards, and downwards. Now, for your exam, you will need to know how standing waves are formed. So, they are formed by simply having a source at first, and this just emits any regular wave. And what happens is this wave eventually meets a reflector or a mirror. And when it hits this reflector, it gets reflected back. So you have a forward wave sent by source gets reflected back. You can see that this forward wave and the reflected wave basically are two different waves. So the two waves interfere. Another word that you can use to describe this instead of saying interfere is that they superimpose. Now, as we looked at in the last video, when waves meet in phase, they constructively interfere, and when they meet out of phase, or completely out of phase, they destructively interfere. And the same thing happens here. So when the waves meet in phase, which means that they have a phase difference of 2 pi, they constructively interfere to form maxima. And when they meet in antiphase, which is a phase difference of pi, they destructively interfere to form minima. So therefore you'll get alternating maxima and minima. There are a couple of necessary conditions in order for this standing wave to form. Firstly, these two waves need to be travelling in opposite directions, and they must have the same frequency and speed. And because of v equals f lambda, they also have the same wavelength. And for standing waves in particular, there are a couple of terms that you need to know that describe the minima and maxima. At maxima, we say that an antinode is formed. And at minima, we say that a node is formed. These are just two different terms that describe maxima and minima. Now, the standing wave doesn't move, as I said, so what that basically means is that the energy is trapped within that specific region. So let's look at our microwave. Now, let's say we have some random chocolate bar in this microwave, and this microwave consists of this emitter, which emits a microwave, and this reflector on the other side. And because this wave is sent from the emitter and it gets reflected back by the reflector, it therefore forms a standing wave. And the standing wave may look something like this. So at this point there's an antinode, here there is a node, and here there is another antinode. And now if we just left this as it is, we can clearly see that at the positions of antinodes there are maxima formed, and at position of nodes, minima is formed. And in the introduction, we said that the amplitude represents the intensity or the power, or in this case, the energy supplied by a wave. So at these points of maximum, we get more heat. And at the minima, we get less heat. So different points on this chocolate bar will heat up more than others. And this means that only certain parts of your food will get heated up. So that is why you insert a rotating plate to evenly distribute the heat such that all parts of your food get heated up properly. Now in this case we're going to be looking at a tube with two open ends, and we are told that a standing wave is formed within this tube. Now what you need to know is that when something has an open end, antinodes are formed at the open end. So we can label that antinodes are going to be formed here. Now harmonics are different kinds of wave patterns that can be formed in situations like this. Now the first or fundamental harmonic is formed in this tube when there is only one node in the middle. And if you have a position of antinode, node, antinode, well then this wave is going to look something like this, or something like that. And here's your regular wave structure. And because we are told that antinodes are formed at each end, we'll start off at an antinode. Now in this first harmonic, you can see that the wave structure ends here. So if this tube was of length L, we can see that half of a wavelength has been formed in this tube. So we could say that the length L of this tube is equal to lambda over 2. And we know that V is equal to F lambda. And if you rearrange and sub this in, we can see that, well, lambda is therefore equal to 2L. So V is equal to 2FL, where F is your fundamental frequency. And therefore, your fundamental frequency is equal to V over 2L. And now you can repeat this to find the second and third harmonics. In the second harmonic, you're going to get an extra series of node and antinodes. So here your second harmonic is going to form at the second antinode position. So you're going to get a full wave forming in this tube. We can see that it has a structure of A, N, A, N, A. So we're going to replicate that and put that in our tube. And if you draw it out, it will look something like this. It can be either one of the top or bottom waves. And if we do the same thing, well, here we can see that in this case, L is now equal to a whole wavelength. So if we again use V equals FL, our second harmonic frequency is going to be equal to V over L. And you can now try this for the third harmonic. And you should get the third harmonic frequency being 3V over 2L. Try this method and see for yourself. Now this time if you had two closed ends, at closed ends nodes are formed. And a good way to remember this is if open is a vowel, so therefore you form an antinode which begins with a vowel. Closed is a node which begins with a consonant, and node begins with a consonant as well. So this time if we look at our wave pattern, we're starting and ending with nodes. So our fundamental frequency is going to form when this pattern is formed inside the wave. So there's only going to be one antinode. So the length here is going to be equal to lambda over 2. And because V is equal to F lambda, we can get that our fundamental frequency for two closed ends is equal to V over 2L. And we can repeat the same procedure for the second harmonic. Well, if you look at your wave structure, our second harmonic is going to have this sort of pattern. So the structure of this wave is going to look something like that. It can be either one of these two waves again. And for this length L, we know that now L is equal to lambda, and because V equals F lambda, our second harmonic frequency is going to be equal to V over L. And this is for two closed ends. If you were to try the third harmonic, and you should do it yourself, you will get that the third harmonic is once again equal to 3V over 2L. Now let's look at the last case where you have one closed end and one open end. So at closed ends we said that nodes are formed, and at open ends antinodes are formed. So let's draw our diagram out again, starting from a node. Well, at this first node position, you only get 1/4 of a wavelength. So in this case, L is equal to 1 over 4 lambda. So because V is equal to F lambda, lambda equals 4L, our fundamental frequency in this case is equal to V over 4L. Well, for our second harmonic, we will get a structure like this. And if we draw our wave pattern, we can see now we get that in this length L, we form 3/4 of a wavelength. Because V equals F lambda, this time the second harmonic frequency is equal to 3V over 4L. And once again, if you try out the third harmonic, you will find out that the third harmonic is equal to 5V over 4L. Now, in the AQA syllabus, there is a practical where you need to investigate the tension on a string and how that affects the frequency or the speed of the wave produced. Now, it may not be applicable to all examples, but it's still a useful practical to know about. So here is the setup. So you have this oscillator, which will vibrate at a frequency that you can set it at, which will then cause the string to move up and down and oscillate. What you have here is a fixed support at the end, and as we know, this wave will get sent from the oscillator and will get reflected back from this fixed support and will therefore produce a standing wave. And you have some known masses added at the end of the string in order to change the tension produced in the string. What you're going to do in this experiment is you're going to vary the tension in the string by varying the mass that you add onto the end of the string. So in this case, your independent variable is the mass, or the amount of mass added to the end of your string. And this is going to supply the tension for your string. And what you're measuring, or the dependent variable in this case, is going to be the frequency of the oscillator. So what you're going to do is you're going to add some known mass to the end of the string. And then you're going to adjust the frequency of the oscillator such that the wave that is produced on the string has maximum amplitude. What that means is the wave will oscillate with largest displacement. The frequency that you're looking for, if you go higher than this frequency, the amplitude will decrease, and if you go lower than this frequency, the amplitude will also decrease. You're trying to find the frequency at which there is maximum amplitude. What you're trying to find out in this experiment is the linear density of the string, or what that means is the mass per unit length of the string, and it's denoted by this Greek letter mu. And the equation for this is given by v, which is the speed at which the wave moves at, is equal to the square root of the tension over the mass per unit length. Now, what you're measuring in this case, as you can see from this wave pattern, is the fundamental frequency. You have two fixed ends, and therefore you can see that in this length L that is produced, which you can measure using a meter ruler, there is half a wavelength being produced between these two fixed ends. And therefore, if you remember from our harmonics derivations, this V can therefore be written as 2 times F times the length between, or the distance between the two fixed ends. So this is equal to the square root of tension over mu. So what you're going to do is you're going to get a lot of different mass results, and this will be in kilograms. And we know through simple mechanics that the tension produced in this string is simply going to be mg. So let's say you use a mass of 0.1, 0.2, 0.3, and so on. This would be 0.1 g, 0.2 g, 0.3 g, and that will be your value for tension. And the frequency at which there is maximum amplitude at the fundamental frequency is going to be determined by you adjusting the frequency on the oscillator. So you can simply read off this frequency value. And now, as with pretty much every practical that you do, you're going to try and find a way to somehow plot a graph using this data, because we want to find out what this value of mu is. So we have now got values for tension and we have values for the frequency. But we can see that frequency is related to tension by the relationship that frequency is proportional to the square root of tension. So you cannot directly plot a straight line graph by plotting frequency versus tension. Therefore, there's two graphs that you can plot. You could either plot a frequency versus the square root of tension graph, or you can plot a frequency squared versus tension graph. And both of these are acceptable. I'm going to go through the latter case of frequency squared versus tension. So what I'm going to do is I'm just going to square this equation. So if I squared that equation, I would get that 4f squared L squared is equal to T over mu. And I want frequency squared on my y-axis, so I'm going to make that the subject by saying frequency squared is equal to 1 over 4L squared times T over mu. So this is my y variable, this is my x variable, and therefore that means that this whole thing here is going to be my gradient. So we can now plot this graph. We have tension on the x-axis and frequency squared on the y-axis, and we can get a straight line and points maybe like that, and we can work out this gradient, and this gradient will be equal to 1 over 4L squared mu. So you can say that mu is equal to 1 over 4L squared m, where m is your gradient. Now if you ended up plotting frequency against the square root of tension and you've got your graph, which is also going to be a straight line, your gradient in this case is going to be 1 over 2L times root mu. So mu in this case is going to be given by 1 over 4L squared times m squared in this case. And both of these graphs are acceptable ways of finding the gradient. Now even if this practical is not on your syllabus, I'd recommend learning it because similar ideas can easily come up in your papers. Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.